Hello, everyone. Thank you for connecting to the monthly seminar of the Working Group on Active B stars. I'm Alexandre David-Duraz, and I'm the main seminar organizer for the working group. And this month, it is my pleasure to introduce to you Dr. Athira Menon. Dr. Menon obtained her PhD in physics and astronomy from Monash University in Australia. Did the first postdoc at the University of Amsterdam, followed by a Humboldt Fellowship at the Argelander Institute of Astronomy at the University of Bonn, and is currently a prize research fellow working on a 3-year grant from the Spanish Ministry of Science at the IAC in the Canary Islands. So today, Dr. Menon will be talking to us about blue supergiants, and with that said, I'll just let her take it away. So please go ahead, Athira.
Great. Thank you very much, Alex, and also thanks to the invitation from the working group on active B stars. It's really an honor to present in your seminar series. So today I'm going to talk about one of the oldest problems in stellar physics, and that is the origin of the enigmatic blue supergiants. So let's get going on this old puzzle. Now, of course, this group does not need a very big introduction to massive stars or spectral types, but it does set the stage for the story. O and B-type stars that are typically on the main sequence are found with companions. That is a fact that we've known through the works of Lucena and others who have looked at various populations of massive stars in the Milky Way and also in the Magellanic Clouds. And what they find is that up to 70 or even 80% of these OB stars are with companions on the main sequence. However, when we go into the more evolved stars, the supergiants, and in particular the blue supergiants, which are the focus of today's topic, that binarity fraction drops. Most of them, nearly 70 or even 80% of them, tend to not have detectable companions with them today. So that gives us the first clue towards solving this old puzzle, which is what happened to these supergiants? Why are they effectively single stars today? And of course, that means when we are building the origin story of these supergiants, there can be two ways in which we can consider them. One is if we think that they were preferentially born as single stars, that means they were just born solo, or if they were born as products of binary mergers. And today we're going to look at both of these angles to solve this puzzle. But before we continue, let me take a moment to thank this great team of people I worked with on this project, spanning a range of expertise from across different countries. From my own institute, they were leaders in observational science relating to massive stars, like Artemio, Miguel, and Daniel Lennon, who directed the observational efforts and analyzing the sample of the stars we're going to look at today. From the other end, the computational team comprising of experts in stellar evolution from Bonn, like Norbert Langer, and in particular, Andrea Ercolino, who's his PhD student and who assisted with the computational efforts of the stellar models I present today, and also Ryosuke Hirai from Monash University. And we're also working in conjunction with experts in 3D hydrodynamic simulations from Louisiana State University. In particular, I'd like to talk about Manus here, who has worked with me since the past year or so, and who is doing these simulations of stellar mergers, which is so important for the work. So that's the team, and these are the people I worked with to publish the results very recently in the Astrophysical Journal Letters. Okay, so what is this observational sample? We have the theories, but we need something to guide us. Some of that sample actually has been published as part of the VLT Flames survey and the Flames 1 survey in 2 separate studies in the past. But what happens is there was no data analyzed for their abundances or surface gravities, etc. So what Daniel Lennon, Miguel, and Artemio did was to collect all of these known early B-type supergiants in the Large Magellanic Cloud and extracted their additional properties. So along with their positions in the HR diagram, we have something like this, which is the abundance ratio, actually in numbers, of nitrogen over carbon and nitrogen over oxygen. So what we have here is about 59 stars. And those are the triangles that you see in this plot. And underneath that are some stellar models, which we will be seeing as the talk proceeds. This is the guiding picture. This is how we used, this is what we used in order to dissect what may be the origins of different types of blue supergiants. And as you can see, it's quite a diverse population, not only in the HR diagram in terms of where they lie with their effective temperatures, but also their nitrogen, carbon, and oxygen abundances. To note a couple of things, I have divided this observational sample into 3 groups. And as the story proceeds, you will see how or what is the motivation to do that. And the second thing is these sample points, which are highlighted with red circles. And those are the helium-rich stars in the sample that are quite enhanced compared to the LMC baseline. So, of course, all of these stars are in the LMC, something I should have mentioned. And in the background are the stellar models that we will see as the story unfolds. Okay. So when we talk about born-alone stellar models, that means these stars are the conventional single stars. There are 3 different phenomena which are typically used in order to make single stars blue. So the first one would be looking at the main sequence stars and considering fast rotating main sequence stars. From nature, we know that the limit for this rotation is typically around 220 kilometers per second in V sin I. So what I did was to consider the extreme of this rotation and see how they contribute to main sequence star stellar models. The other alternatives are looking at post-main sequence stars and the well-known blue loops that massive stars undergo. Now, there are 2 ways they can do that. One is through ramping up the semi-convection in the stellar models, so you can get elongated stellar loops, or by considering the mass loss that would happen in massive stars, which can also generate these blue loops. All right, so here's the picture. You have here the sample, which are the triangles, and you have the background tracks. There are actually 3 sets of tracks. We'll come to that in a moment, but I'd also just like to highlight again the location of 87A's famous blue supergiant progenitor, which is not part of the original sample, but it's very good to also consider that one in any case. So there are 3 sets of tracks over here. And they are the following. We have the main sequence stars, the fast rotating ones, the gray ones in the background. You've got the classical blue loops and the ones that are induced by mass loss, which are higher up in the higher luminosity range. Important to also notice when you're comparing the sample with the tracks are the tick marks over there, which are separated by 0.1 million years. And it gives you a sense of time spent by the stellar models at that particular location of the diagram. So of course, where they're more concentrated, the stars should tend to spend more time over there. So when we look at this picture, what we notice is that most of the blue supergiants, these early B-type ones, are collected somewhat very close to TAMS, that is the end of the main sequence. And the classical blue loops, that is the post-main sequence stellar models from single stars, are not quite able to reach that strength in temperature. They're quite cool and don't seem to spend very long in the effective temperature range that they're interested in. On the other hand, when we look at the blue loops induced by mass loss, well, there seems to be a better relief. There's some intersection with the sample. But what's important to note here is that the mass loss induced blue loops lead to stars which are stripped of most of their hydrogen-rich envelopes. So that means these stars don't have very high surface gravities. I mean, it's much lower than what we observe in the sample itself. So structurally, these high luminosity stripped stars do not have a resemblance compared to that of the observed sample. So the strict star models don't work as well. So one then might argue, okay, so perhaps then these observed stars just may be single stars evolving on the main sequence and making their way towards the end of core hydrogen burning. But then let's have a look at this picture. This shows us the distribution of nitrogen over carbon and nitrogen over oxygen in number ratio. And here you can see why we have split everything into three groups, the sample into three groups. The first group is consisting of stars which are modestly enriched in these number ratios. That may be, in fact, originating from the main sequence stars, but those main sequence models I showed you, the fast rotating ones, don't really go far off and explain the rest of the sample. They only explain a minor fraction. So although morphologically, I mean, from the HR diagram, there's an overlap, they do not reproduce the much higher abundance ratios that we require as the stars tell us themselves. If we consider the very extremes, that means just at the end of the main sequence and of fast rotating stars, yes, at the end of the main sequence and the upper limits possible from classical blue loops, those are the yellow stars in the background, then you might be able to match the second group, which are moderately enriched in nitrogen over carbon and nitrogen over oxygen. So there is some reprieve over there, but then again, one must consider that there are inconsistencies with the HR diagram, for example, with the blue loop stars, and that most massive stars don't rotate as fast as 20 kilometers per second. They are not so fast as that, maybe 80 to 100 kilometers per second. So the second group, you might need some extreme ends of physics in single stars to reproduce the abundances over there. And of course, have also put in the blue loops induced by mass loss, and they're out of the scale entirely because they come from strict stars and don't match anything in the sample. So what contributes to the biggest group in this sample, the third one, group 3, which is nearly half the sample? What contributes to those? And that's where we bring in the picture of evolved stellar mergers. Okay, so the idea of stellar mergers contributing to various phenomena is not a very new one. In particular, evolved stellar mergers, where you have one of the stars of the binary, which has gone past the main sequence, puffed up into a red supergiant with a hydrogen-depleted core and undergoing unstable mass transfer with its companion. And this phenomenon has been used to explain various other categories of stars, like B bracket E supergiants, LBVs, of course, 87A's famous progenitor, and more recently, the fast-rotating red supergiant Betelgeuse, if you believe that it is indeed fast-rotating. All of these have been somewhat well explained by these the stellar merger hypothesis. But I would like to bring our focus now to this particular event, which sets the stage for our inspiration, let's say, to look further into this theory in explaining the currently observed B-type supergiants. Now, 87A, of course, we know was a historic event for more than one reason, but of relevance for us today is the fact that it harbored the first imaged supernova progenitor in history as well. So when we look back at the photographic plates after the event went off in the Large Magellanic Cloud, everyone was quite thoroughly surprised to see that the star that exploded was, in fact, also a B-type supergiant. And there were many ways in which one could create a blue supergiant through the single star hypothesis. We saw some of those phenomena earlier, but none of them could consistently explain the three essential characteristics of this star. Where it lied on the HR diagram, the abundances of CNO derived from its famous triple ring nebula, which we can still see today, and also the lifetime of that nebula, that is how long ago it was ejected before the explosion occurred. So that's where there were alternative theories, and the binary merger hypothesis worked best. And these models that we created during my PhD in 2017 were the first to explain how several diverse binary mergers can lead to the kind of progenitor 87As had. That is, it explained those three characteristics quite promisingly. So that led us to think, okay, so if 87A's progenitor, which also has those enriched nitrogen over carbon and oxygen ratios, can be produced through an evolved stellar merger, would that also explain how the currently seen B-type supergiants have also come about? Let us understand what that merger actually entails in a bit more detail. So this picture here I have built from Natasha Ivanova's PhD work, who did one of the first simulations, in fact, of a giant hydrogen core depleted star engulfing its smaller main sequence companion. So the idea is the following. You have a binary. It starts off with a separation of anywhere between 100 to a few thousand days. And the more massive star leaves the main sequence, puffs up, there is a dynamical mass transfer to its companion. And then the companion, unable to accommodate this mass at such a quick rate, gets quickly engulfed in the envelope of the primary. At this point, we have a corresponding HR diagram on the right. And what you see there is the position of the primary star and the secondary star just prior to the expected common envelope phase. Now, this one here, this diagram has been taken from a detailed grid of binary models spanning several ranges of periods and mass ratios and initial masses. And this was built by Pablo Marchand in his thesis. So the models I'm going to show you now have been taken from very detailed MESA binary models, and they've not been randomly selected to undergo mergers. It's been well informed. And from there, I have built the post-merger tracks. So let's go back to this picture over here. So that's where the binary tracks themselves stop, because in MESA or in fact, any binary code, you cannot really compute the merger or the common envelope phase. Now, from there on, what is expected is the following. When the common envelope phase ensues, and of course the evolution itself is stopped, we are talking about what happens in 3D simulations, or what we expect to happen in theory at least, is that the secondary star begins to slowly but quickly speed up towards the center of the primary star's core. And as it does so, because of viscous drag forces, at a certain point very close to the core, it can get tidally disrupted by the core of the primary star. And this tidal disruption causes the secondary star to be completely shredded. Most of it gets mixed in the envelope due to the turbulence of this merging process. But it is possible that if the stream of material from the shredded secondary star hits the core with ram pressure, it may be able to actually penetrate the core of the primary star itself. And if that can happen, it brings in new hydrogen-rich material to the core and dredges out the ashes of hydrogen shell burning out to the surface of the star. So that is already a bit of a clue to tell you that this mixing of the secondary along with the dredge up can induce CNO products to come up to the surface. And that's how you might expect some distinction from the single star models. Let us actually see how that happens, how we simulated this is very complex picture into 1D, and that's this over there. As you can see, this is the primary star. It's gaining mass from the secondary. If you follow the blue line, you will notice that it became smaller. That was the hydrogen-free core. With the addition of the hydrogen-rich material, it's become smaller. you have now a massive star with a big envelope and a much smaller hydrogen-free core, and that is left to evolve until the end of carbon burning in the core. This particular star lived as a blue supergiant, in fact, for nearly 1.2 million years, but more about that in a moment. So once the star has gone through the merging, you've got a newly born post-merger star. And then, as you saw, it has puffed up. It's become quite big. And then we expect that it rotates quite rapidly because of the merging itself and sheds some mass in the process. We have not personally included rotation yet into our models because of computational difficulties. In fact, that's something we'll be doing a bit later. But rotation can be and is an expected consequence of such a merger. And finally, here you have the full HR diagram. You've got the evolution of the primary over here, just before the merger. This is the merging process we saw a bit earlier. And then it's left to evolve until close to core collapse. Not quite, we only go up to the end of carbon burning, but that's very close to where we can expect the star to explode. In this particular case, the star did explode as a blue supergiant, but that's not always the case. It can change depending on the dynamics of the merging process. Okay, so now what I'm going to show you from here on would be a bunch of our stellar merger tracks that we painstakingly constructed. There are about 40 of them. I'm not going to show you all, just a few. Each of those 40 stellar models from mergers were computationally challenging, and we did it separately for each of the binaries that we selected from that great detailed grid of binary stars from the University of Bonn. But before you actually see that full picture, I'd like to prep you for it, let's say. We will only be looking at the post-merger evolution. So essentially, you will be seeing just the blue supergiant phase and not the full track itself. And that's what will be highlighted in the next few plots. Again, these tick marks are there to guide us for a sense of time that the stars will spend in that particular region. And yes, we can now proceed to see what are the outcomes of these stellar mergers. Okay, so this is the work we recently published. These are all case B mergers. That means the primary star still had a helium-rich core when it merged with its companion. And what you can see is that, very interestingly, the sample intersects quite well with the merger tracks themselves. And they are all over in this region. They're quite hot. And again, they encompass most of where the observed sample lies. This helps us see it a bit better. What really distinguishes these merger-born models from any of the previous single-star ones is the fact that they are core helium-burning stars throughout that entire nuclear burning phase. So the reason these merger models are successful in reproducing the HR diagram positions is because of this longevity from the second longest phase of nuclear burning in any star's life. And that's what is making them agree quite well with the locations of the observed stars. But you might see that some of the stars don't quite overlay with the models. And that's where we can look at the previous set of models I showed you with regard to 87A's progenitor. So our understanding may then be that there's quite a diversity of B-type supergiants that we can expect from stellar mergers. The case B mergers may lead to the hot ones, and the case C mergers may lead to the cooler ones. While the case B mergers are core helium-burning blue supergiants, the case C mergers are core carbon-burning blue supergiants, and may even be very close to exploding. We don't know. So that should cover the range in temperatures observed in these B-type blue supergiants. Let us now come to the abundances. When we look at the abundances, there's a mistake over here. That circle should have been overlaid over here. If you can just give me one moment to stop the share, I'll just correct that very quickly. Okay, great. This is back. All right, so if we now look at the number ratios, we see that, in fact, the highest enrichments in the sample for nitrogen over carbon and oxygen are reproduced almost exclusively by these stellar mergers. And you can also actually see where 87 is progenitalized in over there. So that gives us some sort of additional confirmation that they all have likely very similar evolutionary pathways. But we can maybe even explain a bit more if we also consider the group 2 sample. Some of those stars, as you notice, are helium rich. What's very interesting is that these particular enhancements in helium are not reproducible by any of the single star models that we looked at. These enhancements can be matched only by the merger bond stars. So given their presence and the fact that we consider the uncertainties, that's the error bars in the sample themselves, and if we consider a bigger space in the merging binary scenario, that means if we go down to lower mass binary mergers, we may also be able to explain these group 2 stars, at least some of them, in particular, the ones that are helium rich. So all in all, considering in this nitrogen enhancement, which is a very giving clue, this tells us that stellar mergers may be responsible for a large fraction of the, or maybe the most dominant channel to produce these blue supergiants. I have to bring your attention into this question about the helium as well. And this is mostly an observational question. But the fact is that those helium-rich blue supergiants, as you can see, they're scattered throughout. They're all throughout the sample. But it doesn't seem to make very good sense, because when you have helium enrichment, you also expect an accompanying enrichment in nitrogen over carbon and nitrogen over oxygen as well. And that's not quite the case. So the fact that these helium-rich stars are scattered throughout the sample is telling us that perhaps there needs to be some revision of the way the helium abundances themselves are derived. And it's the other way as well. You have a lot of stars that are rich in nitrogen over carbon and oxygen, but you do not see an accompanying enhancement in helium. They seem to have baseline helium. So this is something that needs to be flagged and something that needs to be worked on in more detail. But to sum up the origin story of B-type blue supergiants, the largest fraction of the sample seems to originate from stellar mergers, because they can explain the very high abundance ratios, or number ratios actually, of nitrogen to carbon and oxygen, and simultaneously also reproduce the surface gravities and the HR diagram positions of the sample. We have a second group, that should be group 2, by the way, a second group of mixed stars, which are a combination perhaps of the most extreme single star models, along with a contribution from the mergers, given the constraints of the sample, and by going down to lower mass mergers. And as I mentioned earlier, also the fact that there are quite a few helium-rich stars in that sample. And finally, if we were to only look for the contribution of born-alone single stars, then that might form only a minority, and they may in fact actually just be main sequence stars that are nearing the end of their lives in this phase of evolution, given their very minor enhancements in these number ratios. So that sort of wraps up the origin aspect of blue supergiants. Now we will move on to the next part, the transients. What do we expect might be the final states, final explosions of these products of stellar mergers? It's actually quite interesting that it's not all of the stars that sustain their blue supergiant nature will end up also exploding as blue supergiants. That can only be said for the case C mergers, which occur much later in the life of the star, and if you have penetration of the core during the merger. So that core penetration, as I mentioned, those dynamics during the merger actually play an important role in determining the final structure of the star before it finally explodes. So for case C mergers, and within the limited range of models that we looked at, core penetration ensures a blue supergiant by the end of its life. And if the star, the secondary star, fails to penetrate the core, but is simply mixed in the envelope, it will just make a red supergiant of that mass. On the other hand, for case B mergers, which were the more recent models I showed you, you might expect to see a blue supergiant explosion in the mass range of 15 to 25 solar masses, irrespective of whether it went through, if there was core penetration or not in the merger. So whatever the dynamics, as long as the secondary star gets shredded and mixed in the envelope, the outcome should be a blue supergiant by the end of its life. If we now look at case B mergers between 25 to 45 solar masses, this picture can change. Core penetration gets you a blue supergiant by the end of the life of the star. But if you do not penetrate the core, then you will get a yellow or even a red supergiant by the end of the life of the star. So you can get quite massive red and yellow supergiants. How feasible that is from observations, we have to see. We're aware of this red supergiant mass problem, but at least theoretically, it is possible to get them from mergers. So we have the possibility of opening a window of several diverse explosive transients from stellar mergers. When you have cool progenitors, red or yellow, that are more extended, then you can get your typical type 2 plateau supernovae, which form the majority of core collapse supernovae from surveys when we look at the survey catalogs. If you have a hot compact blue supergiant star at the end of the life of this post-merger system, then you may end up having just a dome-shaped light curve, very typical of 87A. And so these guys may explode like 87A. But as you can see, that only forms a small fraction of the observed supernovae amongst core collapse events. So there must be something else, perhaps, that's happening. These blue supergiants may be exploding in other ways. But before we get there, let me show you a few examples of the light curves we have looked at with merger bond stars. And these light curve models have been done with very detailed radiative transfer codes. And that one on the left is for 87A, and it's by far the best match with the light curve from any stellar model available in literature. So it's a really good match, and we're very pleased about the fact that it fits so well. We looked at the other two, 1998A, 2006B, and we also get fairly good matches there from these merger-born blue supergiants. Again, light curves are difficult to match if you do it in a detailed fashion, and the fact that merger-born blue supergiants have such a good fit with the light curves tells us that we're getting the structure of the core and envelope and the density quite correctly in order to be able to get these good fits. So it's a good positive thing that we have over here. But since most of the observed core collapse events do not explode like 87A, as I mentioned, up to 5% of them do, is it possible then that blue supergiants may also explode in other ways? That is, are there other transients possible? And that's when we decided to look at these intermediate luminosity optical transients. But these events are relatively faint and they are less energetic than your typical core collapse supernovae. As you can see from the light curves, they don't have your plateau shape or dome shape. They just fall off immediately after the peak. So what we thought was, well, is it possible that these blue supergiants just preferentially go through very low explosive events? Are they just exploding with much less energy than typical events from core collapse supernovae? And so we have here very preliminary results. These light curves have been computed by Takashi Moriya from National Astronomical Observatory of Japan, who I'm working with on this project. So on the left, you have some of the light curves, and on the right, just very preliminary calculations of low luminosity supernovae from blue supergiants. And the first two results that we see here seem to be quite promising and indicate that perhaps by computing a lot more models, we will know for sure that perhaps these blue supergiants may also be progenitors for faint supernovae or these intermediate luminosity optical transients. And that is work in progress that we are looking at the moment, an alternative channel of explosion for blue supergiants. And of course, there's also the possibility that these guys might just be incapable of actually going through an explosion, and they might just be also directly falling back into black holes. There are a number of ways to try and test this hypothesis by looking at the compactness parameter, for example, of these models. We will know for sure about that in the future. And so that's another possibility that for blue supergiants, and quite an interesting one, I think. So to conclude, I will leave you with some future directions for our work. Aside from the supernovae and the remnants we expect from blue supergiants, we're also looking at the other possibilities of elemental signatures, so the heavier elemental yields, not just hydrogen burning products. What else is possible, and how might that be different from single star models? What about the A-type blue supergiants? That is also something we are considering, just looking at the lower mass mergers of binaries. That would be quite interesting too. And besides, we have more lines available, spectral lines available to derive the abundances for a diverse number of elements in these cooler A-type blue supergiants. And of course, there are other samples to look at. There have been Milky Way samples coming in from the ISC, for example, and they are much bigger. So it would be great to work with a bigger sample and then test our models against those. And finally, also consider the rate at which these events occur, which will further help us constrain the number of blue supergiants originating from stellar mergers. I will end my talk with that. Thank you so much for your attention.
All right, so please join me, everyone, in thanking Dr. Menon for this very nice talk and obviously impressive results. So yeah, we'll just take any questions that people might have. So feel free to unmute yourself directly or write it in the chat if that's more convenient. I don't know if you see it, Dr. Menon, but there are many clapping hands emojis in the
No, I don't. Okay.
So yes, Paco, go ahead.
Yeah, hi, Athira. It was a fantastic talk. It's a great job you've done.
Thank you.
Combining all sorts of information coming from analysis and from evolution. I have one question, and it's related to the HR diagram where you put your merged models in the evolution and this, the ones you would expect. and where you
Okay.
found your stars. And so if you can show that.
Yeah, just a moment. Was it this one?
Yeah, that one. I saw
Okay.
that they are, it looks like some of those stars, I only see one blue star at around about 10,000 K. So I wonder if in many of the stars that may be missing is just a matter of selection effect of the stars you analyzed because you concentrated on stars hotter than, I don't know, 18,000 K or something like that. So my question is there a selection effect, or how many stars would you expect according to these models you would require having many stars around 10,000 K? So are those observed? Are there any hints that these stars are there in the LMC? Or I don't know, I
Right.
mean, maybe Miguel or Norbert Pizzavilla can talk about this, because I wonder if these ones which are just formed right after the merging should show the same abundance patterns.
Okay, great. Thank you. Thank you for the great question, Paco. Right, so there is a selection effect. We focused only on the early B-type stars. So B0 to B2, maybe. No, not even B2. Yeah, B0 to B1. That's about the range to which we looked at. So the sample itself was restricted to early B-type supergiants. That's one. And secondly, regarding the question of whether these mergers can produce cooler blue supergiants, I know that's a bit of an oxymoron, but anyway, if it can produce them, then we can look at this diagram over here. And as you can see, these are from KC mergers, and they are populating that region of the cooler part of the HR diagram. So technically it's possible, and the models do predict also a similar level of enhancement in those number ratios we've been seeing in this talk. And so that should be again should separate them from typical single star models. I hope that answers the question.
Yeah. I mean, now if you put both together, it's clear, because you see, you may expect a lot of models between 4.8 and 0 and 5.0, which in the left one in the top down corner and right corner, but you should expect many odd objects in there for 5.2 to 5.8 in the cooler ones. Okay, so that makes sense. Thank you.
Yeah,
and
welcome.
Congratulations. Yep.
Thank you.
Okay, so I think I might have seen Doug who had a question.
Hello, Athira. This is Douglas Guys. Thank you for your wonderful talk.
Hi, Douglas. Hi.
Many years ago, Nolan Walborn was interested in galactic blue supergiants, and he introduced a spectroscopic notation of OBN and OBC stars. And in light of your work here, do you think it would be, is there some connection perhaps that the stellar mergers might represent the OBN class with enhanced nitrogen, whereas the OBCs without enhanced nitrogen might represent the single star population?
It's a very good question, Doug, because Danny mentioned Walburn's work, and we talked about these as well. In fact, that's some of these stars in these in the N over C plot over here. You can see them. They're rich in nitrogen over carbon, and not so much in nitrogen over oxygen, and some of them are kind of outside the equilibrium lines, which are these gray ones. So there are some interesting targets over there, and we really have to look at them in further detail. As of now, I can't answer the question regarding whether these merger models can explain them, but they're certainly very interesting, and maybe there's a whole other evolutionary pathway to form them.
Okay. Are there any other questions for Dr. Menon? Yes, Dietrich.
Yeah, a very, very helpful talk. Thanks a lot for this.
Thank you.
Luminous blue variables can confuse the issue because they move in the HR diagram, so that the position in the HR diagram does not map one-to-one to the physical properties of the star, at least not at all times. And one of the most conspicuous properties, and you showed them, of 87A are the 3 rings.
Right.
And about 15 years ago or so, Nathan Smith and collaborators identified an LBV which also has such rings. Have you analyzed this object?
Is it yes? Is it share 25? If I'm not wrong.
Yeah, exactly. Yes, thank you.
Yes. I did look at it, and in fact, one of the follow-ups that we are also considering is to make a collection of these blue supergiants or LBVs with similar rings as 87A, and consider what might be their nebular abundances. And if they all seem to have such high enhancements in nitrogen to carbon and oxygen, then that's telling us something about a common origin for these stars, which may well be these mergers. So that's definitely something we're also looking at as well. Our suspicion is yes.
And there is also the suggestion by, I think, Yoon and Langer, or Langer and Yoon, for the origin of the rings as a combination of a red supergiant wind, which was penetrated by a much faster blue supergiant wind, which then led to the outer 2 rings. So that would also perhaps suggest a pre-explosion trace of the evolution.
Yes, indeed. And in fact, you're quite right to point it out, because the existence of the rings themselves does not ensure that the star was born through a merger, but the ratios of these elements, this nitrogen to carbon and oxygen ratios, if they are enhanced to the levels that we have seen here, then that can be a better way to dissect the origin of those rings, or at least what happened to that star. The rings themselves, yes, do not ensure that they came from a merger.
Yeah, thank you for your answers.
You're welcome.
Okay. Any more questions for Dr. Oh,
yes,
sorry, go ahead.
Somebody hears me?
Yes, we hear you.
Okay. My name is Danny van Beveren. I have a
Hi,
question
Danny.
for you. Hi, very nice talk. Thank you very much. Now, if you have many blue supergiants that remain blue during the whole core helium burning, did you check if this does not affect population synthesis of Wolf-Rayet binaries?
No, we did not check this. But thanks for flagging that. I think I'm just going to make a note of it. But thank you. I have not thought about it at all, actually.
Yes,
I think
Paco.
Paco has, and Rene.
Okay, yes. Just a quick question, Athira. Yes, if you have so many blue supergiants coming from mergers, did you play the numbers to see how many red supergiants will be there, or systems that haven't merged yet, and do the numbers match with the kind of population you're seeing? Wouldn't you expect
Yes, please continue.
Yeah, I mean, would you expect a very high population also of systems that haven't merged, where you still see a red supergiant? Or is an H issue? I don't know.
We haven't quite run the population synthesis numbers yet, Paco. We are doing that also, and that comes down to the rates at which these binaries end up going through the common envelope phase. We have to do that next as well. And so once we have the rates through which these channels of mergers occur, we can further then try to determine how many blue supergiants or how many red supergiants come from this channel and what their masses might be. And that's definitely something we're doing next as well. I hope that answers the question.
Yeah, thanks a lot.
You're welcome.
René.
Yeah. Hi, Athira. Thanks very much for the talk. Hi.
You're welcome.
I've got a question about binaries. So 90% of the main sequence O and B stars are in binaries and 30% of the supergiant. I take it that the data from the supergiants are also from radio velocity variations. So how does the separation distribution or period distribution compare between the supergiants and the main sequence stars? And does that help you in constraining your models?
Oh, that's a great question too. We're actually looking at that too next. We're going to have some data coming in for these red supergiant binaries, and that's being led by Lee Patrick. And one of the key questions is indeed to look at the separations of these. You're talking about pre-merger binaries, are you? Or the binaries which are currently...
Yeah, I think that I assume that the main sequence stars are pre-binary, yeah.
Okay, yes. Well, we are looking at both of that. I mean, we are looking at also the distribution of blue supergiant binaries and what are their periods over there. And comparing that with our models would be something we're going to do next for sure. That's also quite important, but it's not done yet, no.
Thank you.
Welcome.
Doug?
Hello again, Athira. Sorry, I have just a very basic question. I was wondering about the MESA models that follow through the common envelope phase. And could you comment about how angular momentum is treated during the common envelope phase? Because I imagine that the original binary has quite a bit of angular momentum.
Right. So we make a very simple approximation over here. We just assume that when we have your primary star, and then you've got the secondary, and we are accreting the secondary star with the surface entropy and angular momentum of the primary star at the time of the merger. And then it is accommodated, and we let this star evolve. But for the sake of computational efficiency for our models, we later on turn off the rotation, and therefore the surface aspects of this problem is not something we really consider. But for the simplicity, as I mentioned, during the merging itself, everything is taken with the values of the primary at the surface, both angular momentum and entropy. Does that answer your question, Doug?
Yes, thanks very much. This is an area I'm not familiar with, so I appreciate your answer. Thank you.
Thank you, Doug.
Okay, so next I believe I saw maybe Nidia wanted to ask a question. I could be wrong. I guess not. Any other questions then? So maybe I'll use my prerogative as a seminar organizer to squeeze one in. Of course, you're probably aware of kind of a recent scenario gaining traction that stellar mergers lead to the formation of magnetic fields. So I was wondering if you could say a few words on how this would perhaps affect some of your results, and whether that could maybe go to explaining some of the anomalies with regards to helium.
Oh, wow, I never made that connection, but thanks for the question. We actually had Jolt here a little while ago, who's one of the big experts in this field. Now, we talked about whether we can detect magnetic fields from mergers and the ones that lead to blue supergiants, and the answer was no, because technically it's not feasible to detect the fields around extended stars, or relatively extended stars at least. And as far as the models go for these mergers that lead to magnetic fields, Fabian Schneider is also one of the experts. All of them are related to main sequence mergers. So our hopes for detecting them around blue supergiants are pretty dim at the moment. And I don't think my models can make any predictions about them as well. So if that somehow helps with the helium question, that'd be great.
Great. So yeah, I'll be honest, I don't know that I would be that categorical about the chances of detecting the field, but
right.
It would definitely be hard. I think that's fair to say.
Right.
Okay. So are there any final questions for Dr. Menon? In that case, please join me in thanking Dr. Menon once again for a wonderful talk. And I think the hallmark of great work is that it creates a lot of discussion, which was great. So thank you for that.
Thank you so much. Thank you very much.
I'll just remind everyone that this talk, as well as all previous talks, will be available on YouTube. If you haven't had a chance, or if you have colleagues you think would be interested, then keep an eye out for that. And we'll be announcing next month's seminar relatively soon. It should be occurring in mid-April. So please stay tuned for that. Once again, thank you everyone for connecting. Thank you, Athira, for a very nice talk. And I wish you all
Alex.
a great rest of your day.
Ciao. Bye-bye.